Today, we're going to tackle concept 3, which we're going to cover here in 2 days. So 6.4 is concept 3, rational exponents. This is a no calculator concept. So when we have our test on Friday, which will include concept 3, you're not going to be using a calculator on concept 3. But even though it's no calculator, the hardest thing in this is adding and subtracting fractions. And I hope we can add and subtract fractions, or with a little bit of practice today and tomorrow, we remember how to add and subtract fractions. It's not where I'm going to give you these big problems that I expect you to know factors and perfect cubes and everything of big numbers. So don't be intimidated. It's no calculator. It's really not that bad. So we're going to now start talking about rational or fractional exponents. So instead of saying square root, we'll say raised to the 1/2 power. And then being able to go back and forth from rational or fraction exponents to radical form. And then still, we're always going to be simplifying. So simplifying those radicals, simplifying rational exponents. And that's really the big piece that you'll not be able to use a calculator on. All right, so we'll do concept 3 today and tomorrow, 4 Wednesday, Thursday. Friday, we will have our test. All right, here we go. So this very top line is what you need to know when going from a rational or fractional exponent to radical form. All right, you need to write that down and reread it, study that, memorize it. You need to know this. Okay, so if you have some base A raised to a fraction 1/n, that's the same as the nth root of A. All right, and how I always remember that, I always think, well, A to the 1/2, I know that's the same thing as square root of A. So in my mind, and I said it just a few minutes ago when I was giving an example on rational exponents, in my mind, every single time I start to think A to the 1/2 is the same as square root of A. But in variable form, A to the 1/n, that denominator of your rational exponent becomes your index. And this A under the radical symbol is really A to the first. Well, we don't have to write A to the first, but the numerator of our fraction is the exponent on our radicand. And then A to the m/n, so say now we had 3/4, we would write that as the 4th root of A raised to the 3rd power, which can also be written with this A to whatever power outside of parentheses. So that is equivalent as well. All right, the denominator always goes to the index position every single time. But that exponent on A, we can either write it under the radical or we can write it outside of all of it. All right, so if I had 16 raised to the 1/4 power, well, I know my index is 4. And so this is really 16 raised to the 1st power. 16 raised to the 1st power, I don't have to do anything with that. So I'm trying to take the 4th root of 16. So the 4th root of 16, okay, is there a number that if I multiply it by itself 4 times, it'll get me 16? Yeah, 2. All right, so this, I expect you to do this level of difficulty without a calculator. And again, a way to test it, I mean, the bigger the index is, the smaller your multiples are going to be. So don't be intimidated if it's like a really big number, but then it says like to the 5th root. Well, it's going to be a small number. Okay, 1's never going to work. So you can maybe try 2's, try 3's, try 4's. You'll be able to find it pretty quickly. So don't be intimidated if you see a big number as the radicand, but then also a big number as the index. It's just telling you that there's going to be some small number that you're going to work with. In variable form, so if I went from radical of x, or the 5th root of x, I know that's x to the 1/5. So again, the index becomes my denominator. I can rewrite, and there's nothing I can do with this. 8 to the 2/3 is the cube root. of 8 squared. So again, my property tells me I could also write this as the cube root of 8 entire quantity squared. Because I'm trying to actually, it's easier to keep this as a small number under here. So I know I could have done 8 squared, which is 64. Well, I'm going to use this property. I'm going to bring that squared all the way out and do that at the end. So the cube root of 8, what can I multiply 3 times to get 8? Well, I know that's 2. So now I have 2 squared, which is 4. If you had done it and rewritten this as cube root of 64, you would have got the same answer. Okay? Again, I'm trying to think, what can I multiply 3 times to get 64? I can start with 2. Okay, 2 times 2 times 2. Okay, that only gets me 8. 3 times 3 times 3, that only gets me 27. 4 times 4 times 4, 4 times 4 is 16. 16 times 4, yeah, that gets me my 64. So that would work too. All right. So this kind of breaks it down with smaller numbers. 2 squared is easier than doing cube root of 64, but either way, we'll get you to the right answer. All right, so rewriting in exponential form. Number 1 is a easy one to make a mistake with. This radican is one entire thing. Like I was saying here on this square root of 30x, it is the square root of 30x. It is not the square root of 30 times x. So I know there's a 2 in the index, even though it's not written. This is equal to this entire radican raised to the 1/2 power. All right. Do not write this. So do not say this equals 2x to the 1/2 power. All right, that is not true, because really this is 2 times square root of x, which is not what I want. I want the entire radicand of 2x being raised to the 1/2 power, because this is really, like, if I were to write this back out, well, it just takes me back to where I started. Okay, it's 2x that's being raised to the 1/2 power, not just the x being raised to the 1/2 power. Parentheses are important. Keep that radican together. All right, this one, so my base is b. My denominator I know is going to be 5, and then it's 2 on top. So this would be b raised to the 2/5 power. All right, this one would be my entire radicand, 3x cubed, all raised to the 1/2 power. Ooh, back that up. That is not correct. Okay. What I did there was if it was 3x cubed, which is actually what we don't want. All right. We want this as, this is going to be 3x, 3, we could write it as 3 to the 1/2 times x cubed raised to the 1/2. I was not paying attention to my own advice. Like I said, it's easy to make those mistakes. That cubed on the x does not apply to the 3 in front of the x. So we could break this up and say, well, that's 3 to the 1/2 times x cubed raised to the 1/2 power, or 3 to the 1/2 times x to the 3/2. Okay, now let's go from exponential to radical. So I know my index will be 5, that's my denominator, and then I could write it as x cubed. Or I could also write this as the 5th root of x all cubed. Either one is correct. All right. Number 2, I cannot switch a decimal into radical form as is. I need to write this as a fractional exponent. What is 2/5 as a radical? I've already put the negative up there. What's 2.5 as a radical? 2.5 as a fraction. Joel, what do you say? What's 2.5 as a fraction? There you go. 5/2. All right, so we need to know 2/2, 2.5, 2.5 is the same as 5/2. All right, so now that I have it as a fractional exponent, now I can write this. And again, I don't like to work with negatives in our exponents. So let's rewrite this first with a positive exponent by bringing it down to the denominator. So this becomes 1 over the square root of y to the 5th. All right, and if we were to rationalize the denominator, because remember, we don't like leaving radicals in the denominator. So I would multiply this by square root of y to the 5th times square root of y to the 5th. So on the top, I only have square root of y to the 5th. And in the bottom, I no longer have my square root symbol, and it's just y to the 5th. And we cannot simplify if something's in a radical and something is not in a radical. Those do not mix. Okay, you cannot combine those together. Keep those apart. Keep those separate. And then the third one here, 2 times x to the 1/2. Again, that x to the 1/2 is only on the x. So this is really 2 times x to the 1/2. If you want to write it out there so you don't make that mistake, that 2 is really just our constant multiple that's coming along. We're not doing anything with that 2. So this is 2 times the square root of x. I don't have to write the 2. You don't have to write the 2 in the index position. If you do, it's not wrong. But you can just leave it with the square root symbol. So it'd be 2 root x. All right, let's do a couple more. Now simplifying. So 2 raised to the 1/3. Again, this is without calculator. So we have to try to figure out, okay, 2 raised to the 1/3. Well, I know that's the same as the cube root of 216. You're like, I don't know what I can cube to get 216. Start going through the progression. Well, I know 2 cubed is 8, so it's bigger than 2. 3 cubed is 27. It's bigger than that. 4 cubed we did was 64. It's bigger than that. 5 cubed, 5 times 5 is 25. 25 times 5 is 125. All right, it's bigger than that. 6. 6 times 6 is 36. 36 times 6, might have to do that on scrap paper, but that does equal 216. So the cube root of 216 is 6. So again, as your radicals get bigger, but then if your index is big as well, don't panic. It's going to be a relatively small number. All right, so just start going through the progression, testing each one until you find one that works. This one is really square root of 7 times square root of 7. And so that becomes square root of 7 squared. My index and my exponent are the same, so that's just 7. We could also think about this. Remember, we add exponents. So this is really 7 to the first power, which is 7. So you can think of it that way. When you multiply with the same base, you add those exponents together. Or you can think about it with combining with multiplication. Square root of 7 times square root of 7 would be square root of 7 squared, which is just 7. Or 3, this would be the 4th root of 5 times the 4th root of 125. All All right, don't get this confused from the last concept, the last test, when we were trying to get it to be like radicals. Okay, if our index is the same and our radicand's the same, then we can just add or subtract. This again is multiplication. So this is saying the fourth root of 5 times 125. So this is the fourth root of 625. So we have a big index, we have a big radicand. So we'll start going through our progression, okay? 2 times, so 2 to the fourth power would be 2 times 2 is 4, times 2 is 8, times 2 is 16. All right, I know it's not 2. I'm going to keep going. This one ends up being actually 5. 5 times 5 is 25, times 5 is 125. 125 times 5 is 625. This one would be square root of 3 times the square root of 12. So that's the square root of 3 times 12, which is the square root of 36, which ends up being 6. So again, these are no calculator problems, and these are probably a little bit more of a stretch than you normally do with mental math, but it's not crazy. Like, I'm not asking for ridiculously big numbers that I'm asking you to do mental math with. All right, we should be to at least this level. If these are easy, perfect. These ones are testing you a little bit, that's good. Okay, just continue to practice it. You'll get better and better. All right, let's do a few more. Now dividing with these radicals. So in my numerator, without a radical, I could write this as x to the 3/4 power divided by x to the 2/8 power. Well, x to the 2/8, I could also, that's the same thing as x to the 1/4. If I were to simplify that 2/8. When I am dividing with exponents, I subtract the exponents. When I'm multiplying with exponents, I add the exponents. So this is really x to the 3/4 minus 1/4. And so we end up with x raised to the 2/4, which is the same as 1/2. And you can leave it in exponential form if you want. I mean, I will add specifically rewrite in exponential form or rewrite in radical form. If I don't clarify, if I don't specify either way, I don't care which way you end up your final answer, okay? You could have wrote this as square root of x, and that's still correct. Okay, either one of those I would accept unless I explicitly say rewrite it with a radical or rewrite it with an exponent. All right, this is x to the 3/2 divided by x to the 2/3. So I have x to the 3/2 minus 2/3. We'll have to have a common denominator. If I set my common denominator to be 6, this is really 9/6. If I multiply top and bottom by 3, and I'm going to multiply top and bottom by 2 on this one to end up with 4/6. So this ends up being x to the 5/6 power. If I write this in exponential form, 3 to the 1/2, 3 to the 1/4. Again, all I'm doing is adding. So this is really 3 to the 2/4 plus 1/4. I have to have that common denominator. So this is 3 to the 3/4. Dividing, we subtract exponents. Multiplication, we add exponents. 7 to the 1/2 power times 7 to the 1/3 power. I'm going to have a denominator of 6. So I multiply on this 1/2 top and bottom by 3. So it's 7 to the 3/6 plus 1/3 would be multiplied each by 2, 2 6, 7 to the 5 6. Okay, so just a quick recap of everything that we did in all these notes. Okay, so if I'm given exponential form, I can rewrite in radical form. So this would be square root of x cubed, or we would just write that as square root of x cubed, which also is the same as square root of x cubed. So there's a whole bunch of stuff we could do with that one. Exponential form, this would be a base of 2. My denominator would be 5. 3 goes into my numerator. This one is square root of 8 times square root of 4. This is really square root of 32. I can simplify that. That's the same as square root of 16 times 2. So it's 4 root 2. You could have also tackled this one right here from the start. And you would say, well, this is really 8 is 4 times 2. And so it's 2 root 2. Still would have worked, but then we'd multiply this by square root of 4. So we have 2 times square root of 8. Bring out a 2 again. It would have got us at to be that 4 root 2. So you could have done it. You're simplifying from the start. Either way, you get the same answer. Really, no method is more efficient than the other for this problem. This one, I'd have 10 raised to the 1/2 times 10 raised to the 1/3. Set a common denominator of 6. And so this would be 3/6 plus 2/6, 10 to 5/6. And there's no simplifying I could do with that. This slide is really just to recap everything that we just did. All right, so hopefully we did a lot of examples there, and it just takes practice being able to work with it. But hopefully this has started to ingrain in your mind again. Exponential to radical. I can go back and forth, and I need to be able to do that to get to our final answer. Okay, so problems 10 through 34, 39 through 42. Might look like a lot, 10 through 34, all of them, 24 problems right there, but these go quick.